Inverter. Inverter.
Welcome to clickmyproject.com. The title of the project is Sparsity-Aware Affine Projection Adaptive Algorithms for System Identification. Now we can see the abstract of the system. In general, the problem of system identification involves constructing an estimate of an unknown system given only two signals, namely an input signal and a reference signal. Typically, in the existing system, the unknown system is modeled with a finite impulse response filter, that is FIR filter, and adaptive filtering algorithms were employed to compute an estimate of the response of the unknown system being identified. If the system is time varying, then the problem becomes more involved and includes the task of tracking the unknown system as it changes over time. To overcome this, in this paper, adaptive algorithms for system identification of a sparse system is proposed. This strategy results in two new algorithms. They are the zero attracting affine projection algorithm EZA-APA and the reweighted zero attracting affine projection algorithm RZA-APA. The zero attracting affine projection algorithm is derived via the combination of a L1 norm penalty on the coefficients into a standard APA, that is affine projection algorithm cast function, which generates a zero attractor in the update function. The zero attractor promotes sparsity in the filter coefficient during the update process and therefore accelerates convergence when identifying sparse systems. In this system, it is shown that the zero attracting affine projection algorithm can achieve a lower mean square error than the standard LMS and affine projection algorithms. To improve the performance further, the reweighted zero attracting affine projection algorithm is developed using a reweighted zero attractor. Thus, the performance of the reweighted zero attracting affine projection algorithm is found to be superior to that of the zero attracting affine projection algorithm numerically. Now we can see the flow diagram of the system. To overcome the limitations in the existing system, adaptive algorithms for system identification of sparse systems is proposed. Originally, affine projection algorithms emerged to improve speed of convergence of gradient-based algorithms when the input signals did not exhibit flat spectrum. A common feature that encompasses all affine projection algorithms is the filter update equation, which uses n vectors, that is projection order vectors of the input signal instead of a single vector. These algorithms could be understood as an extension of the normalized least mean square, that is NLMS algorithm. The variable order affine projection algorithms adjust its projection order to their convergence needs and therefore decrease their computational cost. For sparse systems, zero attracting affine projection algorithm and reweighted zero attracting affine projection algorithms based filters are used. In a sparse system identification application, the desired signal is the output of an unknown sparse system when excited by the input signal. The input signal is also used as an input for an adaptive filter with m coefficients to produce an output estimate which is compared to a reference signal d of n. Comparing the zero attracting affine projection algorithm update to a standard affine projection algorithm update, the zero attracting affine projection algorithm has two additional terms which attract the tap coefficients to 0 whenever the magnitudes of the weight vector are close to 0. The reweighted zero attracting affine projection algorithm is more sensitive to the tap with small magnitudes. The performance of the zero attracting affine projection algorithm and the reweighted zero attracting affine projection algorithm or compared with that of the standard NLMS, RZANLMS, and standard affine projection algorithms. Thus, 4 experiments have been designed to demonstrate their tracking and steady-state performance based on their mean square deviation value is calculated. Now we can see how to execute the code. The process is done by using MATLAB R 2013 A version. First, open the MATLAB 2013 version, and then when you open you will find this page. Now copy the location of your source code and paste it over here. Then the source code called coding appears here. Now right click the coding and give run. The process now will run, and you will find 4 different graphs for each experiment 1, 2, 3 and 4 for this process. This is the first graph. The graph is about the simulator mean square deviation for experiment number 1. The graph is plotted for mean square deviation against the number of iteration. Here, normalized linear mean square algorithm, reweighted zero attracting normalized linear mean square algorithm, affine projection algorithm, zero attracting affine projection algorithm, reweighted zero attracting affine projection algorithm, or compared. The graph is plotted according to the calculated mean square deviation value. Here, the mean square deviation value of reweighted zero attracting affine projection algorithm is found to be very less. This is the second graph. This is the simulator mean square deviation for experiment number 2. Here, different algorithms are compared with each other as that of the first experiment. Their mean square deviation values are calculated. Then, this mean square deviation values are plotted against the number of iteration. Then is the simulator mean square deviation for the experiment number 3. Here, different algorithms are compared as that of the experiment number 1 and experiment number 2, and their mean square deviation values are calculated and they are plotted against the number of iteration. Last graph, this is the simulator mean square deviation for experiment number 4. Here, the same normalized linear mean square algorithm, reweighted zero attracting normalized linear mean square algorithm, affine projection algorithm, zero attracting affine projection algorithm, reweighted zero attracting affine projection algorithms are compared and their mean square deviation values are calculated. Then the calculator mean square deviation values are plotted against the number of iteration. Thus, the performance of different algorithms are compared here according to their calculated mean square deviation value, and found that the reweighted zero attracting affine projection algorithm is superior than that of the other algorithms. Thank you for watching.